Now that we're ready to begin recording, we can actually start with data collection. So first things first, we've got our spectral analysis pulled up. We're going to select wavelength versus full spectrum, but first, of course, we need to connect to a spectrometer. And now that it's found our spectrometer, we're going to hit connect. And done. All right, now we can select wavelength. So the first thing we want to do is collect a full spectrum because we want to perform our data collection at the wavelength of maximum absorbance. So we're going to go ahead and hit collect full spectrum, and it will take 70 seconds for the lamp to warm up. Now while it's doing that, we can go ahead and prepare our blank solution. So we have our blank and our cuvette, and we're going to just take our solution and we'll use this to rinse the cuvette. Again, we want to rinse this 3 times, and from here on out, right, this is all going to be hazardous waste technically, because we have the hydroxylamine and phenanthrene in each of these samples. So I want to segregate that from the other non-hazardous waste. Again, the rule of 3 applies, so we're going to rinse this 3 times. And then go ahead and fill with our solution. And you want to try to get the cuvette at least 3/4 full. Make sure it's clean, no drops on the side, and then insert it into your sample. Now we can go ahead and collect our blank, and we want to make sure, there we go. For most cuvettes designed for UV vis, there's 2 sides are not smooth, so you want to make sure that those sides are towards the black sides of the instrument and that your light source is actually going through the 2 smooth sides. We can then hit finish calibration, and it will take a few minutes to calibrate. All right, now that we've calibrated with this blank, we can remove that, but we want to use the same cuvette to collect our full spectrum, right? So transitioning from one cuvette to a different cuvette can cause differences in the absorbance spectrum, so we want to try to keep that constant throughout the entire measurement process. So we're going to take our most concentrated standard, and then again rinse the cuvette 3 times with the solution. Go ahead and fill. And insert the cuvette again. And now we can collect our full spectrum. All right. And once we're satisfied with the result, you can see here that the spectrum is holding fairly steady. We can stop our data collection. And then it will zoom in on our finished spectrum. So you can see here we have a couple of main peaks that we're looking at. We want to collect our data at the wavelength of maximum absorbance, so typically termed lambda max. And we can zoom in well, if it will let me zoom in. There we go. We'll zoom in on our data, and then we will want to find our wavelength of maximum absorbance. So if we scroll to the appropriate region, which appears to be between 500 and 550 nanometers. So we can see here we've got a region where the wavelength the absorbance kind of levels off, right? So it from 512 to 504, it only varies from 0.196 to 0.197. So we're going to select to collect at what we believe is the maximum, which looks to be at 507.6 nanometers. And it's a good idea to practice writing that stuff down. And then we're going to switch our data collection mode so that we are actually collecting now single points, measuring the absorbance only at 507.6 nanometers. All right, so at this point we want to change from doing an absorbance versus wavelength to doing absorbance versus concentration. And it's going to ask us to calibrate again. At this point, it would be useful to have already calculated the concentration of your standards. This will allow you to put this data directly into Vernier spectral analysis, and then that will make your life easier as you go measuring sample to sample. Now, that being said, we will want to actually start our sample curve with our weakest standard instead of with our strongest standard. So we're going to go back to our standard number 1, use a new dropper since we don't want to risk contamination with a stronger standard, and again perform a rinse of our cuvette. And actually, I forgot that when we switch modes, Vernier likes us to recalibrate. So we're actually going to have to perform a blank here real quick. And we'll just use the same blanking solution. All right, insert our blank and finish calibration. And now we have to select a wavelength to collect that. So this is why we collected a full spectrum. Our wavelength of maximum absorbance from our full spectrum was 507.6. So that's what we're going to enter. And of course, it doesn't really want to take decimal wavelengths. So if you recall, the maximum absorbance was actually at 506.4 and 507.6. So we'll go ahead and take the difference between the two and collect at 507 nanometers. And we can hit done. And our absorbance at 507 nanometers is 0 because we have our blank in. All right, so we'll move back to our most dilute standard. Rinse our cuvette 3 times. Fill our cuvette and insert it. And now at this point, the SpectraViz should be actively collecting data. So as you can see here, it's measuring an absorbance value. And it's important to make sure that your cuvette is centered properly. So if you move your cuvette off to the side, right, it's going to give you a different absorbance. So try to make sure that the cuvette is completely centered. Wait a moment, make sure that the absorbance is steady. And it looks like it's wanting to hold steady at about 0.015, 0.016. So at this point, you will hit collect. And now we are collecting data, and we can hit keep to store that absorbance value. And we're going to want to enter our concentration value, which the default is in moles per liter. I calculated these values before. So this is actually 0.000000181 molar. Make sure I put the right number of zeros in there. Yep, all right. And then hit keep the data point. And so we've got our first data point automatically inserted. Now, as a point of preference, I would highly recommend that you also record the absorbance values as you go about the experiment. It is a very sad day when the computer decides to crash and you lose all of your data points. But if you manually record them, then even though the computer decides to not behave, you will still have your data. I speak from experience. All right. Once again, we're going to take our second standard now and rinse. And fill. All right, and then reinsert the cuvette, once again trying to make sure it's centered. And give it a moment to see if the absorbance stays steady. So right now it's reading at 0.084. Looks like it's going to hold steady there. And so we'll go ahead and click keep. Right, and we'll have to enter the next concentration. And hit keep point. Right, and then once again, I recommend recording this data point manually. All right, so then we repeat with our third and fourth standards. Making sure to rinse each standard. Or excuse me, rinse the cuvette with each standard before filling. And it is important as you're going along this, it's possible that you might get a little bit of solution on the outside of the cuvette. Just make sure to wipe that off. You don't want to contaminate the inside of your spectrophotometer, and that will also tend to interfere with the absorbance measurements. All right. Allow that time to settle. And when it looks like it's going to hold steady, we'll hit keep. And our next concentration, which is for this experiment 0.0000127. Hit keep point. All right, and then record our next concentration. And you see here, I did actually make a mistake. So I put in one too many zeros in this concentration, which is why the standard curve is not showing up properly. This is one reason why it is good to always record the absorbance values manually. This will allow you to go back later and create a new standard curve, which actually has the proper information. So with that in mind, go ahead and repeat for our final standard. Going back to our misconcentrated standard here. All right, we can insert this and take our final measurement. All right. Hit keep. And entering 4 zeros this time instead of the 5 that I accidentally entered previously. Keep, and besides, you can see that we have a fairly straight line besides the one data point where I accidentally made it, told the computer it was 10 times more dilute than it actually was. So at this point we can hit stop since we've collected all of our data points. All right, so these are all of our data. This is all of our data. So I've just deleted the data point that I entered incorrectly, and I'm going to enter the new concentration manually so that hopefully this looks a little bit better. Enter. There we go. As we can see now, we have a fairly straight line of these 4 data points. So at this point, really this is all that we have to do for the standard curve. You have the option, you can either just take this data and plot it in your graphing program of choice to get your standard curve, or I believe we can plot the standard curve here. Apply a curve fit, linear, and hit apply. And this will give us our curve, which runs fairly well through the straight lines, and then give us information about the fit of our curve. So it's of the form y equals mx plus b. It will give us the slope, the intercept, the r, which should be close to 1, which at this case we're getting 0.9975, so close, very much close enough for our purposes. So we can consider this a good standard curve. Now, I will recommend again that you write these values down as quickly as possible. First of all, because you don't want to lose this information if something were to happen, and second of all, because you're not guaranteed to have this graphing or this collection software installed on a student's computer. So this will allow them to take the data with them. All right, and now that we've recorded that, we can go ahead and actually measure our sample. So at this point, the sample should have had plenty of time for the color to develop. You can see we have a nice orange color now. We'll use the same cuvette, and we're going to want to rinse this probably several times because we don't want to contaminate our sample solution with our most concentrated standard. That will tend to artificially increase our iron concentration. So we'll want to give this several good washes. All right, now that it's thoroughly rinsed, we can fill it up with our sample solution. And measure the absorbance of our sample. All right. And at this point, the SpectraViz should be recording data. We can go back to collect, or we can simply kind of watch the absorbance as it reads on this screen instead of adding another data point, since we don't know the concentration of this sample. All right, so it seems to like to be about 0.028 or 0.029. So we will go ahead and record 0.029, since that's the number I saw last. All right. So with that recorded, at this point, now we'll be able to take this data. You can take your best fit linear line and use the equation of that line to back calculate and solve for the concentration of your sample. Now note that the data that you get out of this is going to be the concentration in the diluted river water sample, right? So we took 75 mLs of our sample and diluted that to a volume of 100 mLs. So we'll have to apply a dilution factor there to do our final calculation. But with that, we are basically done. There are some more optional experiments that you can do, right? Importantly, our absorbance for our sample does fall within the range of the absorbance for our standards. If for whatever reason your absorbance is too high or too low, then you have to expand your range of standards to include that absorbance value. The alternative, and something that is commonly practiced, is if your absorbance is too low, you can actually spike your sample, right? So I could take a little bit of our 10 ppm stock solution, and I could actually add a small volume of that to our sample, and that would then increase the concentration, and then I would just have to subtract out the amount of iron from our stock solution. But in this case, we don't have to do that, and so we can stop our data collection, and that basically is it for our experimental part.